our next speaker is going to record himself.
Yes.
And he's Marco Badini, and he's going to speak about duality for metrically complete lattice order groups.
Okay. Thank you, Jose, for the introduction. So from the logical motivation behind this work goes back to Stone duality. So Stone proved that every Boolean algebra embeds in the power set of some set X. And actually, Stone proved more than that. In fact, he proved that the category of Boolean algebras and homomorphisms is dually equivalent to the category of Stone spaces. And so having a duality, not just a representation theorem, is something that allows us to easily transfer problems from one side to the other. So, for example, the quotients of the Boolean algebra are in bijection with the closed subspaces of the Stone dual. And okay, this is for Boolean algebras. And Boolean algebras admit certain generalizations that reflect the passing from classical logic to non-classical ones. One of these is MV algebras, which are the algebras of Lukasiewicz propositional logic, which is a many-valued logic, in which, roughly speaking, the two-element set is replaced by the unit interval 0, 1. And some. Okay. So are there? So in Stone duality for Boolean algebras, we have some pleasant features, which we do not have for the whole class of MV algebras. For example, every Boolean algebra is an algebra of 0, 1 valued functions, but we do not have something similar for MV algebra in the sense that it's not every MV algebra is an algebra of 0, 1 valued function with 0, 1 the unit interval. And so for this reason, and for other reasons, we look for dualities for certain subclasses of MV algebras. So this talk will be about a duality for a certain class of MV algebras, but actually MV algebras by theorem by Mundich are equivalent to a category of certain of the structures which are better behaved. It's easy to work with them. And these are the unital abelian groups, and so actually we work in this setting. So we will, I will share with you a duality that we obtained for a class of unital abelian lattice order groups. And again, here, unital abelian lattice order groups are two MV algebras. What R is to 0, 1, the unit interval 0, 1. Okay, so to see what this duality is, let's recall what an abelian lattice order group is. This is an abelian group that has a lattice order, and which is which is translation invariant. So if x is less or equal than y, then x plus z is less or equal than y plus z. So some examples are R with the usual sum, as well as in any of its subalgebras. So for example, Q, or you may take 1 over nz for any positive n. And another example is you take any topological space X, and the set of continuous functions from X to R form an abelian lattice order group with usual with a pointwise defined operations. Okay, little bit of spoiler. It got crazy. Okay, if in the case when X is a compact space, then this abelian group C of XR has the constant function 1, which has a special property, and that is that every element is below a multiple of 1, because by compactness every function is bounded. and this is reflected, can be captured with the notion of strong order units. An element is a strong order unit of an abelian L group G if for any x in G, x is bounded by n times 1 for some n in n. By a unital abelian L group, we mean an abelian L group with a designated strong order unit. So okay. So the logical motivation of this talk is okay. Let's see. Okay, so for example, given a compact, say a Hausdorff space X, the set of continuous functions from X to R is a unital abelian group where we take the constant function 1 as a strong order unit, but also we can replace R with any of its subalgebras, so the continuous function from X to Q, or the continuous function from X to 1 over nz. These are examples of unital abelian groups, and we can also mix these subalgebras, saying, okay, let's take all the continuous functions from X to R, but say in this point I'm allowing the values just to take the function just to take value in a certain subalgebra, and this gives new examples of abelian groups. And Gooder and Handelman characterized some of these unital abelian groups. So, okay, so let's consider the unital abelian group that arise in a certain way. If you have a compact Hausdorff space X, for any element of the space, you choose a subset of R, which is either of the form R or 1 over nz. Okay, and then you consider all the continuous functions which satisfy this unary constraint, namely that for every element of the space, f of x belongs to a of x. So think as every element has its own label, which tells you what values the function might take on that element. So for example, c of x r and c of x 1/2 z, or we can mix. And Gooder and Handelman characterized the unital abelian groups that arise in this way. Okay, these are precisely the metrically complete ones. Now I will define metrically complete, but probably you might notice that here we're not allowing all subalgebras of R, but just those subalgebras of R which, let's say, those are subgroups of R which contain 1, which are topologically closed, or in other words, which are complete in the Euclidean metric. Okay.
Margaret, do you
Yes.
assume here, or can you assume that this AX depends continuously on X, or you make no such assumption?
We don't make any such assumption. And that's a good point. I mean, that's a good point, and this the absence of this assumption is what makes this representation not a duality, right? So, and the point of the talk is to give some more assumption, so to obtain a duality. So, excellent question. Thank you. Okay, and. Okay, so now recall that for in these examples that are in the previous slide, so for example, think of C of x r. The submetric or uniform metric is complete. Recall that the submetric is the following for any f and g functions. You take the infimum of all positive real numbers, such that f minus g is between minus lambda and lambda. So this is a metric, and these guys here are complete with respect to this metric. Any Cauchy sequence which satisfy when any Cauchy sequence converges, and we can rewrite this condition in some equivalent way, which will allow us to phrase this metric in our L group context. So here, instead of taking subalgebras, instead of taking lambda in R, we can take rational numbers, and then we can multiply Q on both sides and obtain this definition of the uniform metric on an algebra of functions. Okay. And so now, before I told you that Gödel and Handelman characterized the abelian group. Let me go back for a second. Not so back. In this way, as the metrically complete ones, now we can define metrically complete. The unisolar abelian groups metrically complete are those where this function from G times G to R, defined as here. And this makes sense in any unisolar abelian group. Is metrically complete if this function defines a metric, first of all, and this happens. It's a metric if and only if the G is Archimedean, if you know what Archimedean means, and moreover, it's complete. In general, this is just a pseudometric. So a known example is Q. In Q, it's a metric, but it's not complete. Okay. So maybe I'll stay here. Okay, and this result is a representation theorem for metrically complete unisolar abelian groups, but as you observed, it's not a duality. And our aim is to make it into a categorical duality. Okay, so that we can use this, we can transfer problems from one side to the other one. Okay, why it's not a duality? Well, it's not a one-to-one correspondence. So, for example, let's consider these two examples. Take a singleton with the label Z. First example. Second example, take a unit interval with all the points with label Z. And now in both cases, the associated unisolar abelian group is isomorphic to Z. Essentially because, well, here it should be clear. Here you take any continuous function from 0, 1 to Z by continuity and connectedness of 0, 1. Any such function is constant. And so in both cases, the associated unisolar group is Z. And so in order to have a duality, we should impose some conditions on these labels so that at least one of these does not satisfy this condition. And this condition is a sort of separation property, not just a topological one. for example, we already have Hausdorffness, but a condition that involves also these labels. And it's a sort of Hausdorffness condition in the following sense. It is the following. Take two distinct elements, x and y, then just as in usual Hausdorffness, you impose that there must exist two disjoint open neighborhoods, U and V, of x and y, such that anything that is left, anything that is outside U and V, has a label R. Okay, so for example, these satisfy the condition because you don't have any two distinct elements, and this does not satisfy it because you cannot separate 0 and 1 in a way such that anything that is left from the two open sets has labels R. Okay, so this will be one condition that we impose on our structure spaces, but it's not enough. For example, and this is something very similar to what Adam asked. Consider these two examples. The same space, which is the one-point compactification of the natural numbers, A. And in the first case, we assign to any point the label 1/2 z. In the second case, we assign to any point, any isolated point, the label 1/2 z, but the accumulation point, we assign the label 1/4 z. But then, what you see is that if you take any continuous function from this space to R, which satisfy all these constraints, so particular, if that in every isolated point it takes value in 1/2 z, then also in the accumulation point it will take value in 1/2 z. And so it cannot take the value 1/4, for example. And so the two groups that we obtain are the same group. So in order to have a duality, we should impose a condition that at least discards one of them. And this condition is a form of continuity. Let's say semi-continuity, meaning that if I have a limit point, then the label of the limit point must be the limit of the labels of the points that converge to it, or smaller. So, for example, here it should it would have been fine if instead of having 1/2 z, we would have z. And one way to phrase this without nets or converging, without nets, is to say that for every n positive, the set of points x such that ax is included in one nz is closed. So let's see why this does not satisfy this condition. Take n equal 2. Then this set here is precisely the set of all isolated points, which is not closed. Okay, and so we have these two conditions, this separation and this semi-continuity. Let's put them in a definition. So normal A space for arithmetically normal arithmetic space is a compact Hausdorff space X equipped with a family of subset of R of the form either R or 1nz, which satisfy the two properties, separation and this semi-continuity. And our main result is this duality, that the category of there's a time the category of metrically complete unital abelian groups and homomorphisms is dually equivalent to the category of normal A spaces and certain morphisms. Where here, let's say the most difficult part of the proof is proving a generalization of Urisohn's lemma that takes into account also these labels. Okay, and that's our main result. Now, under Mundich's equivalence, these metrically complete unital abelian groups correspond to a certain subclass of MV algebras, which admit a slightly more complicated definition. But as a corollary, we obtain that this category of normalized spaces is also dually equivalent to the category of metrically complete MV algebras. Okay, and with this, I would like to thank Jose and Goran for organizing this session, for giving me the opportunity to talk, and thank you also to all of you for being here.
Thank you.